What's up guys, Pete here, and welcome back to ProtoWrite Productions. In today's video, we're going to cover both the electronics and the software for the Universal Test Machine. Now, we're far from finalized as far as the electronics go. Both hardware and software are very much in a minimum viable state right now. There's a ton of additional features that I want to add, both for creature comforts and just general machine functionality, but for where everything is at today, it should be good enough for us to do some initial testing and just see how well the machine performs overall. Now, as far as minimum viable goes, there's really only like two things that I need to be able to test this machine properly. The first is the ability to both read and display data that I collect from the DRO and the load cell, and the second is the ability to use the stepper motors to drive the crosshead, both manually and automatically for testing. As far as I can tell, I think we're actually there. So in today's video, we're going to cover both software and hardware for this machine, at least as it sits today. So let's head on over to the machine and start with the hardware first. Now, as far as electronics go on the machine itself, honestly, there's not a whole lot going on here, but let's start with the I/O first. To actually move the crosshead, I've settled on two NEMA 17 stepper motors. Now, long term, I would love to switch these to proper servo motors with active position encoding and closed loop control, but honestly, that's just going to add a ton of complexity and cost to everything right now that just isn't necessary. So hopefully, we'll be okay with just these normal dumb stepper motors for the time being, and we'll try to add functionality as we go. Now, to actually control these stepper motors, I'm using probably the cheapest, dumbest option that's available, an A4988 stepper driver. Those who've been in the printing space for a while now will probably recognize these. These little guys were the backbone of so many early 3D printers. Now, when I say dumb, I really do mean dumb. There are a ton of really useful features you can get on more modern stepper drivers, things like active current monitoring, lost step detection, and sensorless homing. And these bad boys support absolutely none of that. You do get microstepping, and you can set the current for the drivers, though that's done entirely manually with a literal screw on the board. But again, the name of the game for now is minimum viable, and these definitely fit the bill. Currently, I have both of these stepper motors basically slaved over to one another. I have the step and direction pins jumpered together on the drivers themselves, so they're both receiving identical signals from the controller. Long term, I'd love to have independent control of both of these so that we could do something like automatic tramming for the crosshead, but for now, this much simpler implementation will make everything a lot easier for this initial debugging stage. Then we get to our two main sensors, our DRO and our load cell that you probably can't quite see, but he's under there. Now, the load cell is pretty simple. This particular one is rated for about 300 kilos, which should be good enough for our initial testing. I do have some concerns about its accuracy and repeatability, but we'll cross that bridge when we get there. There's likely going to be an entire separate video just on load cell calibration and characterization. This kind of load cell is a pretty simple device. There's some really great videos out there that go into much more detail on how they work, but here's the basic rundown for you. Inside of the load cell, there's a device called a strain gauge that's basically just a zigzag piece of metal that we use as a resistor. The strain gauge is physically bonded to the load cell itself, and its resistance will change as it's physically stretched or compressed. A clever bit of circuitry called a Wheatstone bridge is then used to track this change in resistance as a change in voltage. Now, this change in voltage is very tiny, so we need to use an amplifier to boost that signal. Then we'd also like to convert this purely analog signal into a digital signal for our microcontroller. To do this, we're using a very standard HX711 chip that both amplifies the signal and converts it to digital. Now, this particular chip does have some limitations, most notably being its sample rate. By default, this chip is only reading at 10 Hz, or 10 samples per second. There is a way to bump this up higher, I think to about 80 Hz, but this also comes with some trade-offs. For our purposes though, I expect 10 Hz to be good enough. Most of the materials we'll be testing will be ductile, so I'm less worried about capturing a rapid brittle failure event where a higher sampling rate would be more necessary. And frankly, given some of the other constraints of the system overall, this should be plenty fast enough. Here at the back of the machine, we have our scale that's being used to actually measure the displacement or travel of our crosshead. Now, this is an off-the-shelf component. It's used to add a DRO or a digital readout to things like manual milling machines or lathes. And basically its job is just to keep track of its position and give that data to the user on some type of graphical display. These are actually pretty slick little devices, and the same core concept behind how they work is also how things like your digital calipers and even the encoders on the backs of servo motors work. While the exact implementation might be a little different, fundamentally what's happening is that inside of this scale region, there are very fine little gradations. Think of like the ticks on a very fine ruler. And inside of this read head is two separate sensors that can detect every time they pass over one of those ticks. Because those ticks are a standard spacing apart, we're able to count those and see how far we've actually traveled. Now, as for why we need two separate detectors in this read head, that's because it allows us to figure out what direction we're moving in. Basically, depending on which detector detects one of those lines first, we can see which way this slide is actually moving. There is some nuance as far as how that reading is actually done, whether it's physically reading things with optical sensors, or it's reading it electronically with things like capacitance, but fundamentally they all work the exact same way. Now, here's where I need to get into the weeds a little bit because I'm really looking for some help here from people who know way more about this stuff than I do. So if you're not here for the super technical stuff, feel free to skip ahead. But for those of you who are in the nitty gritty, especially on the electronic side, please hang on because I have some questions for you. At the most fundamental level, what you're actually reading from this is a series of logic pulses. And normally what you need to do is set up a quadrature decoder to read those pulses, track them, and somehow on the microcontroller side, you're going to actually keep track of how far you've moved and in what direction. This is very readily done. People do it all the time. There are even some microcontrollers that have these quadrature decoders built directly into them. So this is something you can do fairly easily, but it does have some caveats. Because you don't want to miss those pulses, generally, from my understanding, you need to use interrupts to make sure that it is always being read every time a pulse comes through. Now, at least for the time being, I'm going to be using an Arduino to be keeping track of everything, and that only has so many hardware interrupt pins. So if I dedicate some to reading the actual signal from the DRO, I'm not going to have any for things like e-stops, which is kind of important. So I was a little hesitant to try and read the quadrature signal directly. Then I came across Curious Scientist's video where he read directly from this exact style and brand of DRO scale, and he found something really interesting. What normally happens with DROs like this is that the signal that they're going to output over their data cable is just those raw pulses from the detector. And then the actual display itself is going to process that, have the quadrature decoder on it, and figure out what those pulses actually mean. This particular model, though, doesn't do that. All of that computing is actually done on board on the read head itself. And what it's sending over the data cable is actually a serial signal that actually encodes the raw data of where this read head has gone. What that means for us is that if we sniff this cable, we don't actually need to do any of the quadrature decoding at all, because this just sends us a simple, I think it's a 24-bit number, basically, that stores the absolute position of where this thing has moved to. Quick clarification, this is not an absolute encoder, but once it's powered up, it kind of behaves that way. There's some nuance there, we can talk about that later. But the key difference here is that with this style of DRO scale, I don't actually need to do the quadrature decoding myself. This data cable is just always speaking out to the world, hey, I'm at 100, hey, I'm at 100. And so I just need to listen to this cable whenever I want to pull new data from it. That was really interesting to me because on paper that shouldn't require any interrupts, which means I can save those for things like emergency stops or limit switches for travel limits. Now in practice, I ended up needing an entire separate microcontroller anyway, and did end up using hardware interrupts to make sure I didn't miss any of the clock pulses, but this still gives me the opportunity to potentially make the system a little bit leaner because I don't need to do that quadrature decoding. So this is where I want some feedback from people who know a heck of a lot more about this than I do. Which approach is going to be better and more consistent long term? Because I can get different style of DRO scales that don't actually output a pre-processed data value. They just give you the raw quadrature signals. That's also an option. I don't know what's going to be better long term. For right now, this is what I have. This is what I'm using. It works totally fine, but there is some nuance there. I still need a whole separate MCU anyway. It is still using hardware interrupts, although frankly that may not be necessary depending on how you write the code. This is just my limited understanding of it. But please, let me know your thoughts here. Is there a better way we could be handling this? Is this the right approach for how to read these types of scales? Or should we be processing that quadrature signal directly? I really don't know, so please let me know what you think. Okay, the nitty-gritty technobabble is over. Now we're back to your regularly scheduled program. So overall, this machine really is pretty straightforward. There's really not a whole lot going on here from an electronics standpoint. It's a couple of motors we need to talk to, it's a load cell we need to read, and a DRO that we need to read. So overall, interfacing with it should be pretty simple, but there's always a lot of nuance in software. Other than that, I do have a couple of hardware buttons that I have for a couple of key functions, so things like jogging the crosshead up and down, enabling or disabling the motors so I can manually jog or tram them, and things like tearing the load cell and doing some other things are done through the serial commands. Now we are technically missing a couple of important bits of hardware here, specifically some limit switches for end stops. I really would like to have some hard limits set up in here so that if it ever over travels, it will just stop the whole machine. I haven't implemented those yet because frankly most of my testing is happening over the course of about 2-ish inches and it's traveling very, very slowly, as you'll see in a minute. So I'm not too worried about it for right now, but that really is something that I'd like to implement in the future. It frankly has to be there before we can release this to the public. But overall, this is, I don't know, probably 90% of the actual electronics that we're going to have in the final design. Obviously, there's a lot of additional features I'd like to add, so things like closed loop stepper control, using some proper servo motors there, independent control of the stepper motors, fancier stepper drivers so that we can have things like current monitoring and sensorless homing, things like that. But for right now, this does cover most of what the system needs to be. So now that we've covered the machine itself, let's go take a look at the brains of the operation and look at the control board that we've put together for this machine. Obviously, long term, I'd love to get some custom PCBs made for this project, but given how much I know I'll be changing things in these early stages, I've decided to stick with breadboards and perf boards for the time being. Now, I did initially prototype all of this on a breadboard, but for some strange reason, I was having these really weird signal integrity issues. Can't imagine why that was. Anyway, so I did eventually go ahead and just build a custom board off some perf board. Overall, this is a pretty simple setup, but I'll put up the wiring diagram to help make things a little bit clearer. The brains of the operation is going to be the Arduino Uno that I have on the backside here, and this whole thing is basically just a little backpack for it. And before you say it, yes, I know there are probably way better MCUs out there than Arduino Uno, but it's what I'm familiar with, it's what I had on hand, and honestly, for these early stages of development, it'll work totally fine. I know that we're pretty much guaranteed to be trying an entirely different MCU, and probably an entirely different system architecture overall, but again, for right now, this should work just fine. The Uno is going to be our master MCU, so it's going to be orchestrating the whole show and handling basically all of the I/O for this whole system. It's also going to be running our main sketch that's going to be driving basically everything that's happening. The Uno is going to be responsible for reading our load cell values through the HX711 chip that we have over here. It's also going to be responsible for sending our step and direction pulses to our two stepper drivers up at the top. It's going to be reading inputs from various buttons that we have for things like motor enable and disable, up and down, as well as an e-stop button up here. And it is technically monitoring the DRO values as well, although it's technically reading them from the NANO, and the NANO is actually doing the interpretation of what those signals actually mean. Like I mentioned, I needed an entire separate MCU to handle the DRO itself. Basically, the NANO is handling interpretation of all the signals, and it's just making the actual real value available for the Arduino Uno over I2C. Now, everything is hardwired directly to the board with one exception, and that's going to be the micro-stepping pins for our stepper drivers here. These are broken out as 3 pins on each of the drivers, and these need to be pulled either high or low depending on how you want to configure that driver. Now, this could have been hardwired in, and also I could have controlled this in software, but frankly, for how often I'm going to be changing this back and forth and how much additional hassle it would be to control in software, I just left these as pin headers for right now, and I can jumper them across as I need to. And then I did also try to use headers like these for any modular components. So the step sticks themselves are mounted onto actual headers down here, so I can replace those if they ever get damaged, or if I just want to try a different module. And same deal for the Nano, I can just pop him off and on if I need to. Other components like the HX711 board and this little USB header here, those are permanently soldered, but they're relatively easy to pop out if I do end up damaging them. Oh, and while we're talking about headers, quick rant here, this drove me insane. Did you know that Arduinos do not use standard pin spacing? They mostly do, but not entirely. Everything else is the standard, 0.1 inch or 2.54 millimeter pitch, except the gap between the 7th pin and the 8th pin. This is not a standard pitch spacing. This is apparently just a mistake that was made by the original creators on the first gen of these boards when they went off to the fab house that was just never fixed. This is so incredibly infuriating because it meant that all of the pin headers for here needed to be custom bent to accommodate this weird half spacing. It made this so much more tedious than it otherwise needed to be. I get it, this is basically an antique board at this point, but come on guys, please, you could have fixed this ages ago and not broken any real compatibility. Ugh, okay, whatever, rant over. This was very infuriating, but it's fine. It doesn't actually impact anything, it just makes my job a little bit harder. One little quality of life thing that I did implement when putting this board together was trying to use actual headers and connectors wherever possible. So you can see that I've got I think this is mini B or micro B coming off here for the DRO, and so I have an actual breakout board here for that. So no weird jumper cables or anything. For the stepper drivers, for the HX711, I've got actual pin headers that line up perfectly with the connectors that are coming off of those components. So you can see this is the cable coming off the stepper motor, and I've actually repinned this to be able to just kind of plug and play directly into my current pinout here. This saves so much hassle because I know I'm going to be disconnecting and reconnecting stuff on here constantly. Knowing that I can just slide an entire connector on instead of 4 individual jumpers saves a ton of time and effort. It can certainly be a little tedious, especially if you're building the cables from scratch as opposed to just using the ones that came with your hardware, but trust me, it's going to save you so much time in the long run. As far as power goes for this board, the only additional power that's needed is for the actual stepper drivers themselves, and so I just have a simple little barrel jack here that will go to a 12 volt 4 amp brick for now, and then everything else is powered just over USB currently for the Uno. Long term, obviously this will probably get replaced with something else, but for right now, this works well enough. I just have to be tethered to a laptop or computer. Now let's head on over to the computer and show you what's actually running on all this hardware. All right, now it's time for everybody's favorite time of day, code review. Yay! Okay, I know this is going to be pretty dry, and I apologize for that up front. Normally, I wouldn't even include this in the video, but because this really is kind of a community-driven project, and because I'm going to be looking for, frankly, a ton of feedback on the programming side of things, I am going to go through this kind of thoroughly, not quite line by line, but pretty nearly there. So first and foremost, if you find this kind of thing boring, please feel free to skip ahead. I certainly won't mind. I don't blame you in the slightest. But if you are interested in what's going on in the back end here, and especially if you're interested in lending a hand on the programming side of things, then bear with me. I will try to keep this as interesting as I can. Now, before we actually dive into the code, you really can't talk about programming and software development in insert current year here without talking about AI. So I do need to briefly have a little sidebar here and talk about the use of AI in this project because it is here, especially on the coding side of things. Just a very brief overview of what my take on it is, how I think it can be useful, how it can be harmful, and we'll kind of just go from there. I promise we're not going to get too philosophical here, but I think it is an important discussion to have before we dive into the code base. So first and foremost, AI, ChatGPT in particular, is absolutely being used in this code, and I will do my best to highlight very clearly and succinctly which sections are directly from AI, which sections have some massaging from me, and which sections are fully from me, because I do think that distinction is important. And really to kind of kick this off, I do want to have a discussion about basically the different types of use of AI when it comes to programming. I think while there's a broad spectrum of how it can be used, generally there's kind of two extremes that I want to highlight because I think it's relevant here. On the one far extreme side, you have what I consider full-on vibe coding. This is where you're not concerned about the how, the what, the why. You're just telling ChatGPT or whatever LLM you're using, hey, I need code that does XYZ. It spits you out a whole fully finished sketch. You try it out. If it doesn't work, you give it some feedback and you just repeat that process. But during that time, you have basically zero understanding of what's happening, how that code works, and really any of the details about it. That's what I consider like full-on vibe coding, way off on one side of that scale. And to be fair, there is some of that in this code base as well, but I just want to clarify that that is kind of one extreme of how you might be able to use AI for this type of programming. Then on the other side of the spectrum, and I think it's an important distinction to make, you can use AI to basically be a teaching tool for learning code and programming. In this case, you're never asking it to just give you a fully finished, fully defined sketch, but instead you're asking it to teach you about what you might need to use in order to do your development. As an example of that, early on, basically what I did is I wrote an initial sketch and I fed it to ChatGPT and said, hey, here's what I'm trying to do. Here's the code that I have. How does this look, right? Give me some feedback, give me some ideas here. And it looked through it and said, yep, your structure looks okay, but in this particular case, it looks like what you'd want is actually a state machine. Would you like me to write you a full sketch using a state machine? That's where I said, no, please don't do that. What is a state machine? Walk me through it. Show me the structure in Arduino in C++, which is basically what Arduino is running in the background. Show me how it's built, show me the benefits, show me how to use this tool. And had some back and forth with it and was able to teach me roughly how this structure works and that, yes, this is probably the right approach for this particular chunk of code. In this case, though, I'm actually learning how to use a state machine. I'm adding it as another kind of tool in my toolbox. I'm understanding how it functions. I'm understanding when it is beneficial and when it can have problems. And I'm using ChatGPT as a tool to learn how to use this portion of code. And so those are kind of the two extremes that I want to highlight here. On the one end, you can use it as a genuine teaching tool, basically like having a very knowledgeable person sitting over your shoulder who can kind of guide you along your journey. Or you can use it for full-on vibe coding where you understand basically none of what you're asking it to do. And in this case, it's kind of analogous to probably going out to something like Fiverr and just asking someone to write the program for you. Frankly, I think there's a time and place for both options. I don't think either is inherently wrong or bad. I think it just depends on the situation. Kind of a hot take, I know, but bear with me here. Obviously, the most controversial is going to be on that full vibe coding side, but I think that has a time and place. At the end of the day, there are times when the goal is not to learn how to program or to learn how to use these tools. The goal is just to accomplish something else, and programming is a means to an end. And frankly, a lot of what I'm doing here today kind of falls into that realm. My goal is not to learn C++ or to learn how to use an Arduino. It's to build a universal test machine, and this is a means to an end. Now, that being said, I still would like to learn more deeply about what this code is doing, because there are some safety concerns, and obviously this is going out to the general public, so I don't just want to kick something out into the world that I don't understand at all, but I do think there's a time and place for, yeah, this is just a tool, and I want to build a little thing, and that's good enough. For some people, in some cases, I think that's totally fine. And frankly, I think in a lot of ways, this is actually analogous to something that's already done universally in programming, even before we got AI, and that's the use of libraries. We see this all the time. I have some libraries in here for the HX711 and for some push button commands. This is a very common coding practice. Someone has built a tool, a library for you to use that automates, for lack of a better word, a portion of the project that you were otherwise going to have to code from scratch. I would argue that most developers, most programmers out there, do not thoroughly review the entirety of every library they've ever implemented. They trust that it's redundant, that it's built well, that other users have already done some validation on it, and that it works well enough. And they just kind of implement it in their code, trusting that it's going to work as intended. Is that always the right choice? No, absolutely not. For safety critical or security critical cases, you really should do some type of code audit on the libraries that you're implementing. But for most cases, it's just good enough to assume that it's going to work as intended and just implement it into your code base as is. Obviously, apply some common sense, and that goes with vibe coding as well. But I don't think there's anything inherently wrong with just trusting someone else's work, putting it into your code base, and using it as you see fit, so long as you do the right risk management on it. Now, personally, for this project, long term, I'd love to have a much deeper understanding of how the code actually works because it's important to me in this case, especially because there are some safety concerns. But that being said, my passion is still on the overall system architecture and not on the codebase itself. In the long-term project, I'd love to get some help from an actual competent human coder who can help me do the programming on this. And frankly, I'd be okay with not fully understanding what they're implementing, so long as we can have a human dialogue, a conversation about what the code broadly does, how it functions, and what some drawbacks of it there might be. But I don't need to fully grasp every single line of code and how everything is functioning for this project to work. So that's my stance on it. Like I said, AI is absolutely being used throughout the code base here, and I will do my best to highlight that honestly and clearly where it has taken full reins versus where I'm taking some liberties with its output and vice versa. And hopefully that will get us where we need to be in a reasonable amount of time here. Because at the end of the day, again, this project is not about the code, it's about the machine itself and the overall system. So this was a means to an end for me. It helped me get to this stage much faster than I otherwise would be. And over time, we will refine it. I'd like to get much more human input into it, but for now, I think this will be just fine. All right, with that little disclaimer out of the way, let's dive into the actual code review. Now, as you already know from the hardware review side of things, there are actually two microcontrollers involved in this project. We have the Arduino Uno and the Arduino Nano. Now, the Uno is the main brains of the project and handles 90% of everything that's happening on the machine. The Nano, however, is used basically just to communicate with the DRO and pass that information up to the Uno on request. First, we're going to look at the actual Uno's code, because again, it's most of what we're actually doing here. And again, I'll do my best to highlight what is and isn't my original code. This is all written in the Arduino IDE, which in the back end is just basically running C++, and should look very familiar for most hobbyists and tinkerers. Let's start rolling down chunk by chunk and try to give you a sense of what this code is actually doing. Oh, also, one thing that ChatGPT was very happy to tell me is that apparently I have horrible formatting for programming, so I'm going to apologize in advance. Apparently I just don't know how to format code so that it's easy to read and legible, so sorry, it's going to be kind of rough to look at, but I'll do my best to kind of break down what you're actually looking at as we go through it. Okay, so up at the top here, I just have a couple of sections for comments about just future improvements. Frankly, there's a ton in here that I still need to add and document. It's written elsewhere, but it really should be in here so that if someone's looking at just the code, they can get a sense of what's still missing and where problems might still arise, but it's fine for now. Scrolling down from here, we have all of our various libraries, wire for the I2C communication between the two microcontrollers, HX711 for the talking to our load cell, Excel.stepper we're not actually using anymore, so I can probably get rid of this entirely. We'll talk about that later, but I had problems using this library to actually control our stepper motors. And then pushButton.h, this is for actually handling the inputs from our various hardware buttons. I did briefly try to program my own library essentially for doing these push buttons, then frankly realized there was no reason to do that. Let's just use an existing library and save ourselves a ton of hassle. Then we get to some of our definitions. This is for the I2C communication. This hand up in the air, I have no idea what's going on here. This is entirely ChatGPT. I have no idea how the I2C communication works, so this is no idea what's going on here, but apparently it's necessary. Some stuff that we don't need anymore because we're not actually reading the DRO on the Uno itself. I could probably get rid of this later. Our pins for the HX711 and for our stepper driver. Do note we do have the enable pin controlled via software because we do want to be able to enable and disable the drivers entirely. When they're disabled, there's no holding current, no holding torque on the motors, so you can manually backdrive them, which is very helpful for positioning and tramming reasons. Then we go in to define our various buttons through that library for up, down, and the motor enable and disable button. We actually don't need to define our e-stop button here because that's handled entirely separately with a hardware interrupt, but we'll get there in a second. Some declarations for the HX711 library, and now we're going to get into some more interesting bits of the code here. Now, here's just a real quick note. If you see this type of header in the comment section here, this is not me, this is all from ChatGPT. And like I said, I'm going to be very upfront about that. So the whole section here that I'll explain in a second is entirely from ChatGPT. I have a cursory understanding of what's happening here. I roughly understand what we need to do and why it's done the way it is, but this is still way above my general understanding, so bear with me here as I try to explain what's happening. Like I mentioned earlier, I originally tried using the Excel stepper library for controlling the stepper motors, but had a bunch of issues calling that function quickly and frequently enough to not have weird, juddery, interrupted step pulses. And so eventually I had to go through and just manually send the pulses on a regular schedule to the motors directly. This is frankly not that hard to do, and like I said, I understand what's happening here, but I would never have been able to implement it entirely on my own. So ChatGPT was very helpful here. Essentially what we settled on doing is using the hardware timers, so talking directly to the timer that's on board that chip running at however many megahertz, and we're going to use that to time our step pulses that need to be sent off to the stepper drivers. Basically, there's a couple of timers, I think it's 3 total that you have access to on the Arduino, that are able to read directly from the clock on board. And these are just going to sit there and just count their way up until we tell it to do something. In this case, what we're doing is we're using this to time how frequently we need to send pulses to the stepper motors, depending on how quickly we want them to move. So if we wanted to send a pulse every second, for example, we'd have the timer count up until it hits a second, and then we would send a pulse, stop sending a pulse, and let the timer continue to count up. And that really is all that's happening here. It's actually pretty simple. Where some of the nuance comes in is that this number can get really big really quickly. This clock is running at megahertz frequency, which I think is like every handful of nanoseconds it's going to tick up, which you can imagine, even if you're trying to send a pulse every couple of hundred microseconds, that number is going to get huge very quickly. And it'll get so big that it actually can't store that number anymore, and it will actually roll over, which is a problem as far as electronics are concerned. So what we can do is we can apply essentially a scaling factor, and that's actually what we're doing down here with this prescaler. We're telling it to take whatever absolute number it's counting and actually just divide that number by 8. Don't count every tick, but count every 8 ticks, and that's going to keep that number much smaller for us. You do have to play with this number depending on what range the numbers you're looking to compare are going to be in. Right, if you were going to count every 100 ticks versus every 100 million ticks, you might want to scale this differently. For now, 8 seems to work well. And basically all we're doing is we're having that little timer count up, and then when it matches whatever number we've predefined, it's going to trigger some interrupt signal, and then it's going to reset that counter. And that's actually what's happening right here. We're just telling it to reset that counter whenever it meets our condition. Now, what number it's comparing to is going to be defined a little bit later, and it's based off of how fast we want to be driving those motors. And again, we'll show this as we go through the code base here. Now, as far as what we want the microcontroller to actually do whenever we hit that magic number of pulses, that's going to be controlled by this ISR right here, and what we want to do is send a pulse over to the step pin on the drivers. And to do that, we're just going to toggle the pin on the Arduino high and then low. And that's really all there is to it. So again, in concept, honestly very simple. I have a general understanding of what's happening here, but I would not have been able to write this from scratch without a ton more research. So again, AI was very useful here, and because I understand roughly what's happening, I feel comfortable having this code in here. But obviously long term, I'd love to have a proper review done by someone who actually knows what they're talking about. Next, we're going to come to some of our variable definitions. This first section is going to control how frequently we're taking a sample of our load and our displacement, depending on what condition the machine is in currently. You can see I've actually broken it out into be 2 different variables, so we can test at different rates when the machine is idle versus when the machine is under test. And this can be useful for a bunch of reasons. When the machine is idle, for example, you don't really care about getting the most accurate up-to-date data, so I'm polling less frequently than I am during the actual tests. Which, again, doesn't really make much of a difference, but it makes the serial monitor a little less cluttered, and is just a little less taxing on the hardware overall. Now, I mentioned earlier that there are some practical limitations to how quickly we can get this information anyway. The HX711, for example, can only pull at about 10 Hz, or 10 samples per second, so we can't pull much faster than that anyway. Currently, during the actual testing, I'm pulling every 200 milliseconds, which is about half of its sample rate, which I think should be good enough for our purposes. Then we're just defining some more variables for our various DRO and load cell readings. And here we get down to our motor speeds. And again, there's some nuance here that's important to go over. Once again, I've broken this out into 2 different values depending on if the machine is actually running a test or if it's in the idle state. So if it's in the idle state, you might want to jog much faster, for example, because you're just trying to position things and get it roughly where you need it. Whereas during the testing, you're going to want that to be running fairly slow depending on what test you're running, and that might be a little tedious if you're using that for positioning, for example. Now, I've added some extra functionality to the jog speed while the machine is idle that I don't yet have for the testing speed. We actually allow the user to define how fast they want to be moving that crosshead directly through the serial monitor. This is really, really nice because, like I said, you might want to be jogging around at a fairly high rate of speed to get things roughly positioned, but when you're finally dialing in exactly where everything is set up, you might want to slow that speed down. So the user can actually change that on the fly via the serial monitor. Because of that, we also need to set some bounds on what the user actually sets, and so we have an extra variable here to track what the maximum speed is that the user can enter, and we have some checks for that later on in the code. Now for the testing itself, currently that's entirely hard-coded, so it will always run at 10 millimeters per minute currently, and there's no way to change that through the serial monitor. Now ideally, long-term, I would want this to be a variable that you can pass into the argument of what test you're running, so that when you type in 3-point bend test, you can tell it how fast you want it to run, what your limits for displacement or load might be, and other information about how you want that test configured. Currently, it's just hard-coded, which frankly for this early stage is plenty good enough, but long-term I would like this to be user controllable during the actual testing itself. Now I do have some notes in here about the nuance of how quickly we can drive these motors and some of the consequences of that. There's a bunch of things that go into how quickly we can actually control these motors to move. One is just physical RPM limits on the motors themselves, but then two is how quickly we can actually send pulses to the motors. And this becomes important when you start thinking about microstepping. So for those of you who aren't familiar, microstepping is basically allowing us to send partial positions over to the motor. So it has, I think it's 1.8 degrees per step by default, or maybe twice that. No, I think 1.8 is the standard. And if you wanted to, you could send only half a step, so 0.9 degrees, or a quarter step, or I think it goes up to 1/16 of a step. Very useful for very fine control positioning, but you can imagine that if you're moving at a high rate of speed, and now for every 1.8 degrees I need to send 16 pulses, that can add up to a ton of pulses per second that might overwhelm what this microcontroller is actually able to send. Couple that with a 10-to-1 gear reduction, and you can get up to many pulses per second very quickly here, even at relatively low speeds. So we do need to have some intelligent thought about how quickly we want these motors to be moving, and what a realistic maximum speed can actually be. And then I also have some quick notes in here just as far as positional accuracy that even if we had no microstepping because of all the reductions that we have mechanically in the system, you get a very fine control over the actual displacement of everything without any actual microstepping turned on. Then down a bit further, this is where we're actually going to define how quickly we're moving things along. The user's already told us how fast we want to move in millimeters per minute, but we have to convert that to pulses per second, and that's going to be handled here in these two equations. These pulses per second are then converted into an amount of time in between each pulse that we need for that interrupt that we showed you earlier, but that's done in a function a little bit later on. Then we get to some safety related things. So these are going to be our load limits and our travel limits for when we want to stop a test. So if this load value or travel limit is ever exceeded, we're going to stop everything. Now in an ideal world, you'd probably want two separate sets of values. You'd want a set of values that would stop the test, which would just be your end conditions basically. Hey, for a 3-point bend test, we're never going to go over, say, 60 millimeters. So if it ever goes past that, we're going to consider that test finished. And then you'd have a separate set of values that would be your, like, oh shit limits. Like, hey, you went over 500 pounds, you're about to break the load cell, please stop the test. That could be different than, hey, this specimen is supposed to fail after 200 pounds, so stop the test normally after 200 pounds. These are separate sets of limits that have different implications depending on how that test is completed, whether it's actually finished or if it errors out. Currently, they're all the same thing, and frankly for right now that's going to be fine, but this is something I'd like to have a little more nuanced control over later on. Here we're keeping track of the current state of our motor and whether it's enabled or disabled. This allows us to toggle that back and forth. And then we also have a safety trigger here that keeps track of whether or not our e-stop was triggered. Then we get to a really important part of all this, which is the values for the state machine. Now these are just the names of the different states that it can be in. We actually define what those states are and what's supposed to happen later on, but you can get a sense of how we're actually handling the structure of this code right here. Currently, we only have 4 separate states: idle, running, finished, and e-stop, but obviously we can add as many more as we needed to. So we could add a state for calibration, we could add a state for different types of tests, but for now, this is the structure that I have right now and seems to be working well enough. Then we get into the actual setup, so we're going to be defining our baud rate for the serial monitor, we're going to be defining our various pin modes for our various things, in this case the stepper drivers, and moving right along here we have our interrupt pin. Like I mentioned earlier, our e-stop is not on a normal pin, it's on a hardware interrupt pin, so this has to be handled a little bit differently than all of your other pin mode setup. Then we have our setup for our HX711. This is not finished yet. I still really need to go back and recalibrate this correctly. And I'd also like to add the ability for the user to do the calibration in this sketch. Currently you have to pull up an entirely different program in order to do the calibration, and it's kind of hokey. So eventually I'll add that as a separate state where you can put it into a calibration mode, and we'll work on how we actually do the calibration later. For now it's a little hokey and frankly a little bit sketchy. But yeah, this is fairly straightforward. You just need to set a couple of offset values and scaling values that we just don't have good numbers for yet on this particular load cell, but they're placeholders for now. Then we make sure to disable our stepper motors. Currently this is set to 1, which a little contrarily means that the motors are disabled, but either way, you get the point. We're just going to make sure those motors start off just so nothing goofy happens. A little bit of massaging for how the serial print works, making sure we get a boot OK message so that we know that everything is functioning correctly. Some more I2C setup that, again, I'm not particularly familiar with, and enabling our timer that's actually going to keep track of how frequently we need to be sending step pulses. Now we actually start getting to the main meat of the program, the main loop. You can ignore this first line. This is just for some debugging stuff to see how long it takes for a loop to execute. Not really important for right now. But you can see that basically what we start off doing is just read from the NANO, and we'll show you how that actually works later, but just grab the value from the DRO from the NANO, and then essentially do the same thing for the load, where we're just going to query the load cell, the HX711, and see what that current value is. First thing we're going to do is we're going to see if we are currently in an e-stop condition. Now, when the interrupt is triggered, it does do a couple of things, but the main thing it does is flip this little value basically that says, yes, the e-stop has been triggered, and then we can handle the bulk of everything else we want to do in this section right here. From my understanding, you want to have as little as possible in the actual interrupt itself, so we just very quickly turn off all the motors, and then it will force it to enter this state through the rest of the loop. Then we're going to call our function that actually reads for any serial inputs. We'll show you this later, but this is what allows the user to actually interact with the system through the serial monitor. And then here's our state machine that actually handles the various conditions the machine can be in at any given moment. So like I said, for now, we only have 4 states, and currently most of them are going to call entirely separate functions. This is a neat little structure that ChatGPT showed me that just keeps things a little more concise, where we have those functions listed later on, and you just get a much more concise view about all the various states the machine can be in. Now you can see that for some of the simpler states, like the finished case, we're not actually doing a ton in there, so we actually handle all of that right up front, as opposed to calling an entirely separate function. We'll dive into what each one of these states actually does as we get to those functions. Scrolling right along, let's start looking at some of these functions that we've been calling previously. Now this first one right off the bat, entirely vibe coded. This I can take no credit for, this is entirely ChatGPT, but essentially all that's happening here is we're querying the NANO, we're asking it over I2C, hey, what value do you currently have for the DRO? And then we're storing that into a variable that we can use in this context. Then we have our serial input commands. So this is how we're actually handling reading any user inputs on the serial commands. And for now, this is a little bit tedious. You have to kind of hard code everything this way. I'm wondering if there's a better implementation for this, but it works fine for now. But basically, we're allowing the user to input a variety of commands that will have different effects on the overall state of the system. The main thing we let the user do is define the physical state, so idle, run, test start, and test finished, just by entering those commands into the actual serial monitor. So you can see here, you can enter the text idle, and that will actually start the idle state of the machine. We had a couple additional commands. In this case, we have both tear and zero that allow us to tear and zero the load cell and the DRO respectively. This way we can have independent control of those in case we didn't want to have an absolute reading right off the bat. And you can see there's a ton of little cleanup I still have to do in here. There's a bunch of things that I can probably completely remove, but I'm always hesitant to do that entirely. But we'll clean this up as we go through here. Then down here we have where we have the ability to actually change the jog speed that's programmed into the system. So by entering jog speed, we can then tell it how fast we want that crosshead to move while the system is in the idle state. And you can see that we have some protections in here to make sure that we're not exceeding our maximum jog speed that is hard-coded, and that we're not entering some negative value. We could add extra protections on this if we wanted to, but this is good enough for right now. And then just a general error handling script at the bottom here that just says, hey, I don't know what you just told me. The only allowed commands are as follows. Now we're getting to how we actually define the various states the machine can be in and what we want it to do during those states. So the very first one that we have here is the idle state. So this would be when the machine is first powered up or when you're not actively running a test, and it should allow you to jog around the crosshead, view the current load and displacement, change the jog speed, those types of things. One important thing that I had to implement here, and something that I had to learn from ChatGPT, was the concept of blocking versus non-blocking code. So when I initially started writing the rough outline for this sketch, I assumed, okay, we'll use delay. And so we'll delay for whatever our sample interval is, maybe it's 200 milliseconds, and after every 200 milliseconds, we'll read everything and then we'll delay again. Well, the problem with this is that delay basically puts pause on the entire microcontroller for 200 milliseconds, so nothing else can be happening. That includes jogging the stepper motors. And so ChatGPT had to teach me essentially that the better way to handle this is using timers. And so instead of using a delay that pauses the entire system for a set amount of time, we're just going to start a timer, and every time we hit our sample interval, which again in this case I think is maybe 500 milliseconds for idle, then we'll execute a bunch of things. But this isn't preventing anything else from running at the same time. So you can see all we're really doing is every sample interval, in this case I think it's 500 milliseconds for the idle state, I want you to get our various values, print them out to the serial monitor, and that's it. Nice and simple. Then we're going to be checking for if you ever press the button for enabling or disabling the stepper drivers, and that's handled right here. So that just toggles whether or not the drivers themselves are enabled. And then if the motors themselves are enabled, we need to be watching for if the user is pressing either the jog up or the jog down button. And that's controlled again by these two if statements right here that are just looking at those two different buttons and seeing if they're ever pressed. If they are pressed, then we'll handle all of that stepper pulse timing stuff in the background and send pulses to the stepper as frequently as is requested. Then we get to our running state, which in this case is just running a 3-point bend test. Eventually this should be able to handle any number of different tests. I have to figure out exactly how I want the user to be able to call those functions, but essentially for right now, this is just running a basic 3-point bend test, which is just driving the crosshead up into the load cell until we hit some kind of limit. And that's really all there is to it. So we have some things at the start just to check the various state transitions and make sure we're moving into or out of the state correctly. Then we can simply enable our drivers and just start jogging basically. And similar to before, what we're going to be doing is periodically pulling all of our information, so checking the DRO, checking the load cell, and plotting that information out into the serial monitor. Now, a quick note about that. Currently, I have this in a much more human-readable format, so it has nice labels and nice spacing and stuff. But essentially, when we actually want to use this to output actual data, we'll probably trim this down into a more traditional CSV format, so it won't look as nice to a human, but it'll be very easy to import into something like Excel so you can quickly process that data. Frankly, even this wouldn't be too bad to set up some basic ingest logic for, but it'll just be a bit easier if we simplify this a lot and have it be less human readable in the front end. Now for our exit conditions, we have our little checks down here that are basically looking for if either the travel or the load limit are ever exceeded, and that will halt the test and bring it to the finished state. Now, like I mentioned earlier, there is normally a little more nuance here. Technically speaking, if you hit like an actual load limit, that's like an emergency load limit, you probably shouldn't go into the finished state. You should go into some type of e-stop state that may have a slightly different behavior than just, oh, the test is finished, here you go. For example, if the test finishes correctly, whatever that might mean, we still have to define that definition. Maybe you want to then back the load cell all the way back up so that you can easily get the specimen back out. But if you had something go wrong and you exceeded like an emergency load limit, you might not want to move anything. Maybe you just want to disable the motors, maybe you don't want to disable the motors. It's hard to say for sure. We have to do a proper defema to figure out how we want the system to fail in these different states. But this is why that nuance of being able to define a normal completed test versus a test that has e-stopped or errored out, having that distinction could be really useful to us. Then we have our e-stop state. Again, this is pretty straightforward. Just tell us a bunch of messages about what's going on and make sure we can see our current load and displacement. In case there is some issue and everything's under tension, we want to know that there's still tension in the system. And then you can see our actual e-stop ISR here. When you actually press the e-stop button, all it's doing is setting this flag to true, and then what it actually does from there is handled entirely by the checks earlier in the loop. And that's pretty much it. This is a fairly straightforward sketch. It does still get up to a good few hundred lines of code, and we haven't even shown you the nano code yet. But fundamentally, in like verbal pseudocode, right, it's pretty simple. I want to have a couple of different states the machine can enter into or out of. I want the user to be able to do that by either typing a command in serial or one day pushing buttons on a touchscreen. I want the test to be able to jog the crosshead until some limit is hit, either a load limit or a displacement limit, and all the while be plotting that information back to the user. Now, obviously, there's a ton of kind of creature comfort stuff I'd like to add to this that would make this just way more user-friendly in the long run, and a proper GUI would be a nice addition eventually. But for bare bones testing, this is honestly perfect. I should be able to use this sketch to program, theoretically, any normal type of test, and it'd be mostly hard-coded for now, but this should work just fine for testing the mechanics of the machine with a functioning electronic backend. All right, with the code for the Arduino Uno out of the way, we're going to very briefly look at the code for the Nano. And the reason I'm going to say briefly is because, hand in the air again, I wrote functionally none of this. This is entirely ChatGPT, but there is some important nuance that I do want to point out here. I was originally working with ChatGPT to write this an entirely different way, and it was working okay for a while, and then I just ran into a bunch of issues with it, and eventually it just wasn't working at all. And unfortunately, this is a risk you run with vibe coding. I could not grasp why it wasn't working. It looked like some of the bits weren't reading correctly, and it was just very frustrating. Eventually, what I ended up doing is Curious Scientist, once again, coming to the rescue. I'll put a link to his video down below. He had a video reading from these exact same DRO scales, and his method works totally fine. From some initial looking, both in his comment section and from talking to ChatGPT, it seems like there is some room for optimization of his code, but frankly, it seems to work just fine as is. So eventually what I ended up doing was just grabbing his code, feeding it to ChatGPT saying, hey, I need you to bolt on the I2C communication that I need, but I know this works. Please just implement this and use this for now. And it seems to be working great. Like I said, there's probably room for some improvements, some clean, some polishing that we can do here, but that's outside the scope of my capabilities by, frankly, a lot. And I can have ChatGPT do it, but for now, it just doesn't seem that necessary. Long term, I'm sure we'll run into some issues though, so again, if you guys are interested in helping out on the programming side of things, I would greatly appreciate it. Now, because I didn't write this code, I don't want to pretend like I know what it's doing, but I will at least give a very, very high-level overview of what's happening here. As I understand it, from that DRO scale, what we're getting is 2 pins that are sending data over in a bitwise fashion. We have a clock and a data pin. This is some type of serial communication. Again, I'm kind of talking out of my ass here, so apologies, but I want to at least try and give a little context. Clock pin basically just keeps track of the pulses, so you have a steady signal to read from, so you can keep everything in time, so the microcontroller knows when to read and what values it's looking for. And then the data pin is what's actually going to send over a 0 or a 1 of our data. This is a 24-bit data stream, although if I remember correctly, the last 2 or 3 are useless, and the first bit is just like a start bit, so it's just saying, hey, this is the start of the command kind of thing. And then the 20th or 21st bit is a sign bit that tells you which direction things are moving in. And basically, all that those bits of data are storing is just a number. It just stores a number. As soon as you power up the scale, it decides that wherever it is something, let's call it 0, and then it just counts pulses as it jogs along and keeps adding to that number. I think we have run into some issues where that number will roll over for some of the longer DRO scales. For some of the shorter ones, it doesn't seem like as much of an issue. But essentially, all this is doing is it's looking for that clock pin, looking for that pulse that comes over that says, hey, the signal has begun, and it's just going to read, and it's going to store those bits in memory, and it's going to convert them into a number we can actually use and read, and it's going to make that available for the Arduino Uno. And at a very high level, that's all this is doing. Again, I want to give a huge shout out to Curious Scientist here. He has been a huge help in this project. A lot of his old videos are just absolute gold mines for all types of really interesting information, but especially for this type of work as well. Like I said, this is pretty much work just plug and play, which has been incredibly helpful because having to rebuild this from scratch is so outside of my comfort zone and so outside of my knowledge, this would have taken ages to get right. And as we saw, even with the help of ChatGPT trying to write it from scratch, that was a nut that we just could not crack. I could not get it to fix the issues that we were seeing. We got real close, but we just couldn't quite get there. So having a functioning code base that we know works was such a time saver and a huge help. So thank you again. All right, that's the really boring code review portion out of the way. If you stuck with me, I appreciate it. And if you didn't, I can't say I blame you. So thanks for hanging with me. Let's actually now go back to the machine and show you what you actually came here to see, which was the machine actually moving with this code. All right, now let's show you guys a little preview of what this should all look like when everything is tied together. You should be able to see the serial monitor display overlaid on screen here. It's a little hard to film all of this at once, but hopefully this is getting the point across. From the serial monitor, we're outputting a bunch of information from the machine. From left to right, we have the displacement reading from the DRO, that's in millimeters. We also have our current load reading from the load cell. This will eventually be in whatever the user wants, kilograms, newtons, pound force. For right now, it's not calibrated at all, so you can ignore the absolute value that it's showing, but you will at least see that it is responding to changes in force on the actual load cell itself. We're also outputting the current motor state. This is whether or not the motor drivers are enabled or disabled. This is really useful because if you disable the drivers, you're able to back drive the motors, so you can manually jog around the head for tramming or just for moving things around. But when they're enabled, they will actually have holding torque and they'll keep the crosshead in place. And then the last thing we're showing is your current jog speed set for the crosshead. This is user configurable, so you can actually enter a command in the serial monitor and change how fast you want the motors to jog. This is super handy because if you're trying to move a large distance for initial setup, it's a real pain if it's moving really, really slowly. But when you're trying to do fine final positioning, it's really nice to slow that way, way down so you get really nice, minute control over everything. And I am just noticing that those units are entirely wrong. They're supposed to be millimeters per minute, not millimeters per second, but the point's the same. We do also have a number of different serial commands that we can issue, so let's show you a couple of those right now. Like I mentioned, you can control the jog speed, so I can enter in jog speed and let's say 100. And we'll see that value now changes, and as we'll show you in a minute, that does actually change how quickly you're jogging. We can also tear out our load cell reading, so if we type in tear, we'll see that that zeroes out our current load cell. And similarly, we can zero out our displacement as well by typing in the zero command. And these, of course, can be controlled automatically depending on what loop we're currently in. Now, I mentioned you can control whether the stepper drivers are enabled or disabled, and I have that tied to a hardware button currently, so if I toggle that button, you might be able to hear the motor starting to whine as that holding torque is engaged, and you should be able to see that state has now changed. Yes, it is a little bit backwards from what you might intuitively think, the 1 versus the 0, but it doesn't really matter, it works just the same. Now let's bump that jog speed back up and actually move around a little bit here. All right, so we're up to 400 millimeters per second. Let's engage our motors. And let's actually move around a bit. And just to show that jog speed does work, let's drop that considerably. Let's go down to, say, 50. And if we move now, you can see that everything is moving much more slowly. Now let's show that load cell moving. First, we're going to move our jog speed back up a little bit, so we'll go to about 200. And we're going to position ourselves up a little bit closer to that load cell. I do have to be a little bit careful here because the load cell isn't calibrated yet, it is possible we could overload that load cell. It's only rated for about 300 kilos. So I do have an additional little force gauge underneath that. That's just a little hydraulic force gauge like you might use for calibrating a vise. This just gives me a ballpark of how much force I'm applying so I don't accidentally break anything. But with this positioned, let's now drop down our speed. Let's go with 50 for now. And if I slowly start creeping this in, it's going to take a minute, and now we should be contacting right about now. Almost there. Oh, there we go. You might be able to see that needle slowly starting to creep up here. And likewise, you should be able to see that load cell reading increasing. Again, this is not accurate. It's not calibrated at all, but this does at least show you that yes, everything is working. We are able to get a load cell reading. And just like that, we're actually up around maybe 300 pounds of force right now, which is kind of awesome actually. And we'll just back this down off. And we'll see that force drop back off. And let's just disable that motor. For now, the user is going to initiate different states of the machine by just entering commands into the serial monitor. Eventually, this could be done with buttons or some other UI, like pushing virtual buttons on a touchscreen. But for now, we're just going to type in whatever command we want. In this case, run is going to bring us into our little mock-up of a 3-point bend test. This is just going to jog the crosshead into the load cell until we hit either a displacement or a load cell limit. Now, I don't have either of those limits configured correctly for how not calibrated the load cell is and how not set up this is for a proper 3-point bend test. So we are going to initiate this, but we're going to stop it by issuing an e-stop command. So if I hit enter, you can see that we very, very, very slowly start energizing our motors and moving everything along. And if I hit the e-stop, everything stops and we get an error message on our screen telling us, hey, we're in an e-stop condition, please bring us to a different state. In this case, we'll go back to the idle mode. And now we're back in idle, and we should be able to jog everything around like we did before. And that's pretty much it for now. This is a fairly straightforward setup. Obviously, we'll have to add a bunch more states for the various different types of tests we'd like to run. And ideally, I'd like the user to be able to enter in arguments for what conditions those tests are going to be run under. So being able to dynamically set things like your load limit, your displacement limit, how fast you want to run the test. All of that should be able to be configured just directly in the serial commands here. Or eventually in a proper UI, depending on how we actually interface with this thing overall. For now, though, this should be good enough to do some actual testing. The only caveat is that I do have to get the load cell actually properly calibrated before I can safely run those tests. But functionally, the bones of the sketch are there and should be able to run any normal type of test at this point once that calibration is done. Obviously, there's no real upper limit to how complicated we can make this. We can add a ton of additional functionality and a ton of additional information to display to the user throughout the testing procedure. But for right now, with the somewhat limited hardware that I'm running off of currently, and frankly just my own limitations in knowledge with this kind of stuff, this is probably going to be where this project sits from an electronics standpoint for the next few iterations. But of course, if any of you tech-savvy viewers out there would like to lend a hand, I'm more than happy to hear how we can improve the UI UX of this system overall and see what we can get implemented. So there you have it, guys. We are pretty much there with the electronics to begin actual testing on the machine. Now, unfortunately, before we actually get there are a couple of hardware things I still have to do. I still have to actually build all of my test fixtures, which you can see a little teaser of right here. We are actually getting pretty close, but there's still some refinement we need to do there. And I have to actually calibrate everything. The DRO, that's not too bad, but the load cell, there's some nuance there. So we definitely have some more work to be done first. With that said, though, it finally feels real. The thing's alive, it's moving around of its own power. We're finally in the home stretch of at least the V1 of this machine. Obviously, we still have a ton ahead of us, but we're making some great progress here. Now here's where I do want to reach out and ask you guys for your help and your advice on this. Obviously, software is very much not my strong suit, and I've had to do my best just to cobble together what little I do have here. and there is a ton of additional features and functionality that would make this system so much easier to use and so much more versatile that frankly is just kind of beyond my expertise for right now. And that's where I want to reach out to you guys in the community and see if anyone's interested in lending a hand. In the description of this video, I have a link to our brand new Discord server. This is where I'm going to be posting much more frequent project updates on this and any other projects I happen to be working with, and where hopefully it'll give you, the community, a chance to collaborate and help me on this project. So if you guys have any interest at all in either staying more up to date or in actually lending a hand on this, which I would greatly appreciate, then please feel free to check out the link below and join the Discord server. I will eventually be making all of these files and all of the documentation available on either GitHub or some similar platform, but until things are a little bit more refined, we're probably going to be distributing this just through Discord links for right now. So if you do want to get your hands on the initial CAD files or any of the initial stuff here, do me a favor, join that server and drop me a message. Now, as far as next steps, like I already mentioned, there's two big things still waiting. The first is going to be all of the various test fixtures that we have to design. I already have some progress started on that already. And then the calibration of the load cell itself. There's a lot of nuance there and a lot of techniques that we're going to have to try out to make something that is versatile, effective, safe for everybody to use. So there'll definitely be a video on that as well. So make sure you're subscribed to catch those videos when they're released. And if you want to be as up to date as possible, be sure to join that Discord server because that's where I'm going to be posting all of my regular updates that aren't going to make it into the normal YouTube cut. Thanks again for watching, guys, and I'll see you in the next one.